So we've been talking about some famous mathematicians and their part in sort of the development of calculus. We began with Zeno, ancient Greece, who challenged infinity and said the numbers weren't good enough. Archimedes, I would say one of the best mathematicians of all times. His inventions are still used today. He used the method of approximation. And then a long time ago, there was a little bit of a dry spell in serious development of calculus. And then we recently talked about other key players. The second video was Cauchy and Weierstrass. They were cleaning up mess on something that had already occurred right here. That's what today's video is about. There's going to be a big boom in development right here. They were kind of making the literature sound. And also Bolzano and Fourier had similar goals. Bolzano and Weierstrass were similar in sentiment and temperament and goals, making sure that we're aligned with the truth. And Fourier was just this savage scientist who made observations about the world, about heat, and really was a key player in the wake of and after the aftermath of the French Revolution. But what were these guys so concerned about, and what were these guys predicting would occur? That was the birth of calculus, which occurred around here, mid-1600s. And two key players were responsible, or at least usually attributed to be responsible to the birth of calculus. So these guys are literally why we have this class. Let's see who they are. Let's meet them right quick. Of course, this is probably no surprise, but we have Isaac Newton. Isaac Newton was born in the mid-1600s. He was born Christmas Day, which is kind of something fun to remember. Christmas Day, and this is the same year that a famous predecessor, Galileo, died. So it's almost like Galileo immediately passed the baton. Galileo had huge contributions to physics. He died and sort of passed the baton to this guy, Isaac Newton. Isaac Newton was an English scientist. In his grade schools, he wasn't very interested in science or like developing the scientific world, but this is kind of funny. It's not funny, but he got bullied a ton in elementary school, and his own sort of revenge against his bullies was he said, you know what I'm going to do? I'm going to get way better grades than all of you guys so that you're not even close to the grades I get. And yes, indeed, he did. He absolutely began crushing academics. He really taught himself for most of his years. He was intensely private, mostly because he had like a year in Cambridge and he was studying under his professor, Isaac Barrow. Here, let me write that. Isaac Barrow. And Barrow was really at the cutting edge of the development of some fundamental ideas of calculus. And he had Isaac Newton, one of his students. Isaac Barrow had Isaac Newton, both Isaac, kind of interesting, one of his students in his class. And then plague broke out, and Isaac Newton went to hide in his bunker. And those years in Isaac Newton's house, as the plague was running around, the bubonic plague, I think it was the second round of the bubonic plague, the Black Death, were some of the most fruitful years in all of scientific history. This guy is famous for inventing calculus. He is one of the players that really invented calculus in those years of being alone. He contributed so much thought to the development of calculus. He really thought of things in the context of motion and change. Up until him, the world was static, or the study of the world was very static, and he really pushed the scientific world to notice that we cannot keep having a mathematical framework that only caters to a static world. After all, the world around us is changing all of the time. So he was a prolific scientist, really saw the world in a changing fashion. He saw the world as a bunch of motion all at once. He thought sort of in terms of quantities flowing in time. He had special names for things, but the big thing that he put a name to was this thing called the derivative. And this is something we've talked about. The derivative. And this is really how quantities change as time changes. He didn't call them derivatives, though. This is kind of funny. He called them fluxions. Shoot. I hope I'm spelling this right. I'm pretty sure this is right. He called them fluxions, and he called like variables like X or Y, he called those fluents. So he had his sort of own words for these ideas here. And he actually came up with this idea of the derivative. How does some dependent variable change as some independent variable changes? And what he was concerned about is how does it change at instants of time rather than over some sort of change in time. The world so far had some sort of literature for, let's say, how position changes as time changes, but Isaac was wondering how it changes or how something is changing at an instant. For instance, his main context of the derivative was instantaneous velocity. He was concerned about how position changes as time changes, but not over some time interval, rather than that at an instant of time. So if he dropped a ball off a building, he wanted to know how fast that ball was moving, or how fast that ball was, moving, like 5 seconds into free fall, at precisely 5 seconds into free fall, not from 5 seconds to 6 seconds or something like this. And he implicitly used this idea of limits that he found in prior mathematics from people like Eudoxus, or the method of exhaustion from Archimedes. He used this to develop this framework of calculus, and he invented this idea of the derivative. He called them fluxions. He was kind of like a goofy dude. He was very, he took great pride in his work, and he did not like it when it was challenged by anybody. To that degree, if you kind of challenged him as a scientist, he was very angry, and he soon got prestige. He was master of the Royal Mint, held high academic positions, and with those positions, he sort of exploited them if you were a scientist that opposed what he was saying. For instance, Robert Hooke is a famous sort of nemesis of Newton, because Hooke challenged Newton, and I'm pretty sure Newton had all of the portraits of Hooke burned, so to make sure none of those were alive. Anyways, and he's also kind of just he's a little bit snarky, and he felt like he was right. In fact, he was very also religious, and he thought that his noticings of calculus and the world around him were his almost, he was like translating the language of God. He really thought he was getting closer to the language of God with his studies of calculus. He's mad smart. He was obsessive, secretive, combative, very suspicious of people. In fact, his paranoia kind of brought him to his early death. But it's hard to emphasize overall how much that Isaac Newton has contributed to the scientific world, specifically through this idea of the derivative, and also to the relationship between the derivative, which is really the slope of a graph, to the area under the curve of a graph. That is the fundamental theorem of calculus, and you will learn that in your next class. There's so much I can talk about this guy. Here's some of his actual writing. I'm pretty sure that he was teaching us how to make a sundial. And here's this is him working on light and optics, which is also one of the many areas that Isaac Newton had great success in. Overall, it's hard to overemphasize how much Isaac Newton has done for the scientific world. Hands down, don't let anybody tell you different, Isaac Newton is the best physicist to ever walk the planet, and indirectly one of the best mathematicians to ever walk the planet. Again, that's rarely challenged, but you'll find some people that challenges it. Okay, so who is this other player? Over here at a different part of the world, in Germany, we had this other player named Leibniz, Gottfried Wilhelm Leibniz. He was a little bit younger than Isaac Newton, just a few years. He was a lawyer, diplomat, historian, and mathematician. He was a lot more charismatic than Isaac Newton was. Isaac Newton was actually very sort of introverted and secretive and took great pride in his work, and he didn't want, like, he was too scared to publish in worry of negative feedback, where Leibniz had more charisma and he wasn't nervous to publish because he already had prestige. And he was willing to just tell people what he thought. And this got Isaac Newton in a little bit of trouble because Leibniz published his first works on calculus before Newton did. And Newton threw a fit because Newton said, no, I came up with all this 20 years ago. You can't take credit for what I did, but Newton, you haven't published anything because you were too concerned about public backlash. Leibniz, he didn't have any sort of ill will towards anybody. He wanted to keep the peace, but Newton was so combative that Newton wanted everybody to know that for sure Newton was the inventor of calculus. Most historians these days say that both of these guys simultaneously invented calculus. Leibniz, very genius, very good at illustrating his ideas and demonstrating what he found in journals. He was constantly publishing. Here's some of his actual writing right here, and this is emphasis on just like a summary of calculus results. And what you'll notice is that these symbols that we see in his writing are these symbols that we use today. So this is the guy, when we write the derivative, that looks like this, dy dx, or to talk about like a position, or excuse me, velocity, dr dt. How does the output change as the input changes, or how does position change as time changes? This is contributed to Leibniz, and we haven't stopped using his notation. There's this symbol right here, this long, this symbol right here, this like elongated S, that simply means area under a curve, or it's the sum of a bunch of small areas, and we still use that. That is what we call the integral. So calculus as a language, calculus as words are really attributed to Leibniz. Leibniz notation and his really core ideas are also the core ideas of calculus. And his notation stuck with us for the past, 400 years. Brilliant mathematician. Would not stop talking about his calculus, and the calculus that absolutely 100% changed the world. So why are these two guys special to this week in particular? This week is the introduction to the derivative. Newton thought very physically in terms of motion, time, and velocity. Leibniz was very symbolic. Newton delayed publishing. Leibniz published early and very clearly. People say that both of these guys invented calculus independently. Newton technically did do it first chronologically, but Leibniz was the first to publish it all. Britain, which was huge in the scientific world, backed Newton because he already had position there. But literally everybody else backed Leibniz. So it's pretty much England versus the rest of Europe. And the feud slowed British mathematics for quite a while. Because people were too concerned about who had the priority for the invention of calculus. But why is what these two guys found so important for this week? Newton answered, what is instantaneous change? That is what he was answering, and that is what we are studying in this class. Instantaneous change. How does something change instantly rather than over some sort of change in time? Leibniz answered, how do we compute instantaneous change and communicate instantaneous change? Together, what they created was the modern derivative. Calculus was born from motion and notation. Calculus was born from study of motion. That's what this guy was concerned about. And clear notation. Notation, which is attributed to Leibniz. Both of them had the same core ideas. The derivative was not invented simply for mathematics' sake. It was invented to understand change, motion, and dependence. Calculus began as a battle between ideas, really, and not as a sort of a polished system. There was intention with calculus. Newton wanted to better understand the world around him, so calculus was a means to an end for Newton. Newton wanted to study physics, and he invented calculus in order to do so. In order to study physics, you have to understand motion and how things are changing as time changes. The mathematical framework to do that was calculus, so that's what Newton invented. So these guys both really are attributed to inventing calculus, in particular the derivative. And just to see, like, kind of, to finish this video off, just to see, like, how many places this invention of calculus and this invention of the derivative is useful, I wanted to talk about some famous derivatives. I'll do this with white. Famous derivatives across disciplines. So this derivative is not only useful like in a mathematical sense, it's so widespreadly useful that almost every single degree you can get in a school or in a university somehow involves the derivative. I'm about to name drop a whole bunch of famous ones. So that way, this part of the video, you guys, whoever you are, whatever your discipline is, I'm really trying to emphasize to you, this invention of calculus, this invention of the derivative is useful to you. So famous derivatives across disciplines. There's the obvious discipline. This is why the derivative was invented, and that is the discipline of physics. The first famous derivative is velocity. Velocity itself is a derivative. It's denoted like this, v of t, which what velocity is the derivative of position. With respect to time. It's denoted like this, Leibniz notation, dx dt. And with all of these, I'm going to tell you really what a derivative is how some quantity changes as some other quantity changes. So I'll say it the first time. Velocity is how position changes as time changes. And these are all instantaneous. All right, so this is how position changes, to see it. How position changes, we kind of want to read this like that. How position changes as time changes. That's what velocity is. So if you want to know, this is useful because it tells us how fast and in what direction an object is moving right now. Instead of over some sort of interval of time, it's an instantaneous velocity rather than the average velocity, which had already been invented for a while. All right, let's stay in physics. What other derivatives are famous in physics? There are so many, but let's do acceleration. Indeed, acceleration is the derivative of a derivative, and acceleration is, by definition, the derivative of velocity. In other words, it's the second derivative of position, which means there are many ways to say this. One way to say it is how velocity changes as time changes, or how the rate at which position changes. Yeah, that's hard to say, but this derivative would be saying d squared x, well, it looks like d squared x dt squared. That's, again, Leibniz notation. And this would be how velocity changes as time changes. Okay, famous one, super useful. This is where Newton really hit the jackpot. This is useful because it explains why motion changes, or how motion changes and why forces are felt. Acceleration, of course, is the core. There's a core relationship between acceleration and force, and you guys probably know this, but that is Newton's second law. F is equal to mass times acceleration. All right, and speaking of which, there are many other interpretations. Force itself is a derivative. Okay? Force is a derivative. Looks like this. F of t. And that is the derivative of this other quantity that we call momentum. right? And of course, that is the same thing as m times acceleration of t, or dp. How momentum changes, this is momentum, how momentum changes as time changes, okay? So Newton's second law, quite literally, can be emphasized or can be written as this. A force on an object with respect to time is how the momentum of that object is changing. Momentum is simply mass times velocity. You'll learn that when you take physics. In particular, force is how momentum changes. Momentum changes as time changes. So for all of these, I don't know if you picked up this part at the bottom. I'm going to assume I'm saying how this changes as time changes. So sometimes this part changes, sometimes this part changes. So this reads how momentum changes as time changes. What else? We got power, also in physics. What is power? Power is how energy changes as time changes. This W stands for work. So power is how work or energy, transfer of energy, changes as time changes. All right. So those are like the famous ones in physics, but it's not only physics that we see these derivatives. Let's go to engineering. Engineering and electricity. Super famous ones here. So the first one, off the dome, let's see. Not off the dome, I'm looking at notes. Electric current. And that is denoted like this, I, and it is the derivative of charge. This Q is charge, dQ, dt. Of course, this is how charge changes, or electric charge changes, how electric charge changes as time changes. Most of these are as time changes. In fact, I'm pretty sure all of them so far have been as time changes, but we're not forced to do that with derivatives. The independent variable, so here's the dependent variable for all of these, and this is the independent variable. We are wondering how electric charge changes as time moves on, but sometimes the independent variable isn't time, but something else like position, and we'll see some examples. Okay, so electric current is wildly useful because it determines, electric flow, heating, signal strength. Those of you that'll be taking engineering, you'll get super used to this derivative, electric current. There are others. We have electric field. That's a derivative. All of these are derivatives. So there's just a boom with this invention across scientific disciplines. So what does the electric field look like? We denote it with an E, and that is the derivative of potential, electric potential. And as I was mentioning, not always is it the case that the independent variable is time. In this case, the electric field, the independent variable is actually position. So this is how electric potential changes as position changes. It's very often denoted in Leibniz notation, dV dx. And again, that is how electric potential, that V, not to be confused with voltage, we really run out of symbols here, as position changes. So again, we read this as how electric potential changes as position changes. I'm trying to cut out words to make the video a little bit smaller. This is a long history video we got going on here, but I'm really trying to emphasize how many times we see the derivative in science and just across disciplines, not only just science. Okay, so let's see other ones. In engineering, you'll get used to this one. You'll see this one a ton. This is called induced voltage. This is famously known as Faraday's law. Faraday is a beast. One of the more recent scientists. His contributions are crazy. You'll learn about him when you take physics and engineering. So induced voltage, this one's fancy. We got this epsilon. This is the notation for induced voltage, and it is the negative derivative of flux. Okay, I'm doing my notation backwards here. So the negative derivative of flux. Yes, indeed, this is flux. And we're back to time being the independent variable. So, I mean, I should mention why these are helpful. The electric field, that is a derivative. And, like, who cares? Like, who cares about the electric field? So this explains how voltage differences create forces. So applications here are very widespread. We have induced voltage here. Like, why is this useful? It explains how changing magnetic fields, so changing magnetic fields can generate electricity itself. So this is wildly helpful. So this is how... Okay, so wait, where am I at? Magnetic flux, that's what that is. Changes as time changes. And you'll learn more about what magnetic flux is. And there are many more I can talk about. There's capacitor current, which is a special kind of current, which is how voltage changes as time changes. But I wanted to go to a different discipline. Let's go to, this is crazy, we can go to economics even. How are derivatives used in economics? / finance, which is, I mean, this is helpful for all of us to know. You got to know how to deal with your money. There's a famous word. If you're going to talk to an economist, they have a special word for the derivative, and that is marginal cost. Marginal cost is a derivative, famous derivative, and it measures how total cost changes as quantity produced changes. So let me get the notation down here. MC stands for marginal cost, which is the derivative of a cost function. Q is the typical independent variable used for quantity produced. And of course, Leibniz notation, dc dq, dc dq. And this is how total cost changes as quantity produced. Changes, which is super helpful. And there's another kind of like similar function, and that is marginal revenue. An economist will help a firm or some sort of business make decisions based on their study of this thing called marginal cost. And there's a specific way they do that in relation to marginal revenue, which is also a derivative. So marginal revenue, MR, and that is the, of course, derivative of a revenue function, dr dq. And this is how total revenue changes as quantity sold changes. Changes. So those of you that are into economics or trying to get a degree in economics, what you'll learn is that there's this profit function. So P of Q, I'm pretty sure there's a different symbol for that, but that is simply revenue minus cost, and that's how much money you're making. And this is a function that an economist will help some sort of business maximize. They want to make this as big as possible. And we use calculus and derivatives to do that. In particular, by studying the marginal cost and the marginal revenue, if you can force these two things to equal each other, that means that your company is in the best place possible, making the most profit. Okay, so let's see. There are other things like profit growth, interest growth, like profit growth. Here, I can just write it down. Profit growth. Famously, you use pi. That's d pi, dq. and that is how profit changes as output changes, interest growth, all of these things. If you're an economist or into finance or studying finance, these are derivatives that you have to deal with all of the time. This concept of the derivative is prolific. So this would be how just money changes pretty much as time changes. Okay, so where else are derivatives seen? I'll only do a few more subjects, maybe just one more. Biology / chemistry. Just all over the sciences, you guys. So we have, for instance, population growth rate. And it's denoted like this. N prime of t is equal to dn dt. So we have, this is really, some people call this Newton's notation, and this is Leibniz notation. Newton didn't use this, though, so I don't know why it's called that. This would be how population size changes as time changes. We have others. We have reaction rate. If you're a biologist or a chemist, you're going to use this all of the time, which is the change in the concentration, chemical concentration, as time changes. So we have reaction rate. I'll do it like this: D products as time changes, and this is the change in chemical concentration as time changes. Okay, so I should always try to emphasize why we care about any of this. I mean, this is useful because it predicts population expansion or decline. This is useful because it measures how fast biochemical reactions occur. Way useful to a chemist or a biologist. And there are many others, like obvious one, there's like heart rate change, how heart rate changes as time changes, how neural voltage changes as time changes. Derivatives are all over the sciences. So I think I'll shut up because I could just keep going on like how derivatives are seen everywhere. But these guys, we really have it to them. We got a hats off to these two, Newton and Leibniz. I wish I could get this all on one screen, but I feel like in the actual video, the text is going to be too small. So I'll put it kind of like this. All of these are examples of the derivative in the sciences, and we see that this concept of the derivative, which is how some quantity changes as some other quantity changes, depending on each other. Some dependent quantity changes as some independent quantity changes, and they're all instantaneous. We want to see how an object is changing instantaneously, and we see this across all of the sciences. Hats off to Leibniz and Newton for giving us this tool of the derivative, which is a core tool in the study of calculus. The rest of this class, we're going to get used to how to use this, and we'll see it applied, and we'll see it in the context of mathematics and calculus itself.